So we're going to look at an unstimulated resting neuron or muscle cell, which is the same thing as a muscle fiber. So versus a stimulated neuron or muscle fiber, and what the difference is in the membrane potential, okay, and what happens. So we're going to start with the resting one, the one that hasn't been stimulated. So what is a resting membrane potential? So what you're seeing up here, that's the resting membrane potential. So remember, the outside is positively charged and the inside is negatively charged. And do you remember which positive ion was out there? Do you remember? It was,
What?
remember when we were talking about sodium and chloride and potassium? Do you remember what?
Was it potassium?
No, it's sodium that's on the outside.
Wait, isn't potassium on the inside?
Yeah. So remember, these little red ones are supposed to be sodium.
And that's chloride.
And that's chloride, and then
And
here on the
potassium.
inside, you've got potassium. So sodium is out here on the outside, right?
Mm-hmm.
And what sodium wants to do is, do you think sodium wants to come in
No.
to the inside?
Yeah.
Yeah,
Oh, yeah.
like really badly.
Oh, yeah.
Yeah, like super, super badly, sodium wants to come in. And there are two reasons sodium wants to come in so badly. The first reason is, do you see any sodium on the inside there? No. So sodium is in a higher concentration on the outside. So based on its concentration gradient or chemical gradient, it wants to come in. And the other reason is, what charge is on the inside? It's what on the
Negative.
Negative. And sodium is positive. And so that's the other reason, right?
Yeah.
Because opposites
Attract.
So sodium wants to go in really, really badly for two reasons. Its concentration gradient and its electrical gradient, that opposites attract. So this is called the electrochemical gradient for the sodium ion. So electrical and concentration pull that favors movement of sodium into the cell. But when the cell is resting, is sodium allowed to go in?
No.
No, and that's because who's not letting sodium come in?
The thing, the pulley thingy.
The
The
plasma membrane.
Yeah.
That's what this
the
that's what this is here. Okay, so the plasma membrane isn't allowing sodium to come in when it's resting.
Because there's that thing that comes and puts it back.
Yeah. So it's not allowed to come in because plasma membrane is relatively impermeable to sodium. And what you were saying, that sodium-potassium pump actively transports any sodium out of the cell that dared to come in. It gets pumped out.
It's risk taker.
I know. So that's what's happening when it's resting. But if all of a sudden a neuron or a muscle fiber gets stimulated,
Yeah.
then there's a brief increase in plasma membrane permeability to the sodium. So it's like the plasma membrane isn't so strict anymore, and it's like, oh sure, you can come in, sodium. And will sodium come in if it's allowed to?
No, yeah.
Yeah,
of course.
because it wants to come in really, really badly, like really, really badly. Because like I mentioned here, it's negative on the inside, so it's attracted to the negative inside, and also because of the concentration gradient. So when the neuron or the muscle fiber is stimulated, the plasma membrane briefly, like it's not that nice, so only for a really, really short time, it increases the plasma permeability to sodium. And that means that they're like these little channels, and they open up, and they say,
Like
okay,
a moat.
yeah. It's like a little bridge for the moat. And it's like, okay, you can come in, and you can come in, and then it'll close it up again, okay?
But how will it get back?
Because of the pump. The pump has to say, okay, everybody, now you have to get back out. But while it's being stimulated, it lets it come in. And do you think the sodium comes in really, really fast?
Yeah.
Yeah, because it's like, oh my gosh, here's our chance, we can come in. So they all come rapidly in. So there's a rapid net movement of sodium into the cell, down its electrochemical gradient, and that actually changes the membrane potential on the inside. The inside becomes less negative because all this positive sodium is rushing in. So if positive comes in and it's negative, it's going to become less negative. And in fact, what happens is you decrease the polarity across the plasma membrane. So it's not polar, means there's positive on the outside, there's negative on the inside, then it's polarized. But the moment you allow sodium to come in, then it's not as polarized anymore, and you call that a depolarized plasma membrane. So when the plasma membrane's nice and lets sodium come in and becomes permeable to sodium, the plasma membrane becomes depolarized. You don't have that separation of charge. And in fact, when enough sodium comes in, so when a lot of sodium enters, you actually get a reverse in the membrane potential. So look there. What's now the inside? Do you see if is it positive or negative on the inside there?
Positive.
Right, and before it was negative. And
because they're only potassium.
Right, and now
potassium's negative.
No, it's potassium's positive.
What?
Yeah. But you have all these sodiums coming in. There's some proteins and stuff in here which makes the inside negative.
Oh, okay.
Okay. So, and you know what potassium's going to do in the meantime?
They're gonna go over to the other side.
They're going to go over to the other side. Do they want to go over to the other side as badly as
No.
sodium wants to come in? No. They don't want to go as badly because the other side is positively charged, so they're kind of repulsed by that. But they do want to go outside because of their concentration gradient. So sodium wants to get in really, really badly because, and potassium wants to go out but not as badly as sodium wants to come in. It's like, okay, fine.
Okay, let's go.
So when you have all this happening, sodium coming in and potassium going out, this rapid depolarization and actual polarity reversal, you have what's called an action potential. Okay, so I brought a picture here. So this is where the book comes in. So can you kind of zoom in
Zoom.
on that little drawing there? So over here it's showing, so looking at this picture, what you're looking at is an action potential. And what's happening is here it's resting, so it's a neuron, so it's resting at negative 70 millivolts, so that's what it means. On the inside it's negative 70 millivolts is the potential. And then all of a sudden there's some sort of stimulus. And what's going to happen is that stimulus is going to cause positive ions to come in, and see how it goes from negative 70 to negative 55. And that's because, so it's getting less negative because positive is coming in. And then even more sodium is going to come in, and see how it's getting less and less negative to the point where it's actually zero. So now it's not polarized at all. There's no difference between the charge. So it's depolarized. And here it's showing that so much sodium comes in that the inside actually becomes positive. Right. So sodium came in, it's positive, and now it's potassium's turn. So potassium is leaving the inside of the cell. So as potassium leaves, because potassium is positive, if you're measuring the inside now is becoming more negative. And that's because the potassium went out. So that's called repolarization. So that's what's happening, and that's an action potential. And again, it's just because of the movement of basically the sodium and the potassium. So I'm going to bring this back. So neurons, what happens when neurons have an action potential is that it's going to cause what's called a